today is something like a review about problems on the binomial, on the normal distribution, on the on the exponential distribution, and I'm also going to do some problems like the ones that we did. That actually there's one thing that I discovered that we haven't done, and this is to talk about covariance and the correlation coefficient. So what is covariance now? Suppose that you have two random variables. Whatever I say applies for any type of random variables. But precisely, I want to make I will make use of it only for discrete random variables. And I'm doing this for your convenience. I don't want to have you do integrals, which are complicated and stuff like that. I want to keep it easy. What I'm saying, the general definitions I will say apply for everything. So suppose that I have two random variables, then I can calculate the expected value of x times y, and if you're not too intimidated to see this symbol, this is double integration. That's the only time that you see integrals here, so don't worry. This will be x times y times the joint density of the two functions. And exactly what I'm doing here is something which can be done in a more general way. This is the joint density. Whenever I want to calculate the expected value of a function that involves both x and y, mixes x and y, pretty much like their sum or their product, then I use this particular integral. Now, if x and y are discrete, of course, things are simpler because the same thing does not require the integral notation, but it requires a double sum. So you put the values of x, you put the values of y here, you would sum x times y times, again, the joint PMF. So this here was the joint density, here's the joint PMF of x and y. So this is joint again, but PMF, probability mass function. And the covariance of two functions, of two random variables, is a quantity that, of course, doesn't make a lot of sense to you right now. It's defined via this formula, and I think everything is okay. That looks a little bit better, but the battery is not. My laptop is fine, but the projector is dying. It's zombie. It's a zombie's projector. I don't see much there. Anyway, and always we do the sanity check that we are recording. You don't want to end up the recording and have recorded nothing. So this is the covariance. And what does that mean? Well, apart from the mass, which is a measure of normally, a measure of it's something that involves a little bit of formality here. That guy, the expected value of x and y, which you saw me defining here, is trying to see how much coincidence there exists between the values of x and y. In a sense, this is what it's doing in practical terms. Therefore, the important thing is that when I go and define the so-called rho, which is the correlation coefficient, and that's the covariance divided by the standard deviations. So this is a standardized, and this is something like a cosine. So like a cosine. So that's how it works. That kind of cosine function, what does a cosine of an angle does? If you have two line segments, and here's the angle, phi, what does the cosine of phi measures? It measures how far apart from overlapping they are. If they are, for example, orthogonal to each other, if the other vector gets this position and the angle is 90 degrees, the cosine is going to be 0, and of course the inner product will be equal to 0. That's exactly what covariance does. Covariance is an inner product. If we look at it, it's an inner product which is trying to see how much information from X is captured at the same time by Y. Or in other words, how much the values of X are being influenced by the way the values of Y are being taken. So this is exactly what covariance is. And we want to have a standardized measure, a standardized, like I would say, a normalized measure. Here, if we wouldn't standardize, that's why this, to divide by the standard deviations of X and Y, the covariance is a process of normalization. And normalization means the following. Suppose that I want to see, let me give you a very simple example. Suppose that you want to see if a person is overweight or not. What are you going to do pretty much? You're going to put them on a scale, okay? You put them on a scale and the scale says 300 pounds. Well, 300 pounds. But if that person is 5'10", of course, that person will be very wide this way. We have taken the height in the opposite way, perpendicularly to the proper axis. But if the person is 6'5", or 6'6", then that's a reasonable weight. You don't have an overweight person. You have a person with a normal weight, although nominally the weight is very big. That's exactly what I mean by normalization. So you have to see the weight in comparison with the height. Exactly, we have one measure for this. This is called BMI, the body mass index. The body mass index is trying to standardize whether you have to standardize everybody to a common scale so that you know whether they are obese or skinny or they have a healthy weight. Exactly the same thing is being done here. You want to devise a measure to see how much coincidence there is between the two random variables, X and Y, and that's exactly what the correlation coefficient does. So this rho is called correlation coefficient, and it takes values between -1 and 1. And if the values are the values that are closer to 0 means less influence, more or less, about the values, about X and Y. Where if the values coincide and they go close to 1, it means quite a bit of coincidence of the values. So this is the correlation coefficient, and the absolute value of it is less than or equal than 1. Now, how do I calculate this? We'll do it in an example, and in the process of doing this example, I will also solve the problem that you had in the homework, in one of the homeworks. Yes.
0 on the other side.
0 on the left-hand side. Yes, those one on. Now that I need to make one more moment here. Here, those standard deviations can never be 0. They can be 0 only if the random variable is not random at all. It takes the value 0 only. There's no randomness there. If a random variable takes the value 0, it's euphemistically random. Randomness means variation. So, change of values, in other words. So those are always going to be positive. Those are standard deviations.
And you said that it can take the correlation coefficient can take values
Between -1 and 1. It's like a cosine. This is not something that can easily be shown. It's called the so-called Cauchy-Schwarz inequality, and I'm not going to show it. All right? You don't need to, you just need the fact. Don't worry about other things if I don't worry about the other things in this course. Keep it simple. All right? Now, what is very important is to know the following. Okay, we mentioned about independent random variables, where x and y are independent. X and y are independent if the joint density or the joint PMF is the product of the marginals. That separable product of the marginals, as I write it here. And what I'm writing, what I'm showing here, exactly, says that, you see, the marginal of x depends only on the values of the random variable x. You see only x here. Whereas the marginal of y depends only on the random variable, on the values of the random variable y. So in the right-hand side, you don't see the values being jointly considered, but you see them separately considered. You see this kind of separability. That's why you have the product here. So that means independent. So those are the marginals here. And they can be PMFs or densities or PDFs. But those are the marginals. So that means independence. So if we have independence, then there is another property which I'm not going to prove. The expected value of the product of the two random variables is equal to the product of the expected values. This is true only if x and y are independent. It can be valid in other cases, but not necessarily. So you need independence to be able to assert that. Although you don't need independence for another formula, which is this other formula, that the expected value of x plus y is equal to the expected value of x plus the expected value of y. This second formula works always, where this formula requires independence. So this works always. Okay, those are very important formulas that I will be using a lot today. So let me also mark them a little bit in my red boxes here. Independence means that. Independence requires this. This formula requires this. This is valid always. Okay? So, I'll go back to that. If we have independence then between the two random variables, then what do we have here? Look at this formula up here. The covariance of x comma y is the product of the two is equal to the expected value of the product minus the product of the means. But then you have this identity. So what that implies, if you replace this with the right-hand side here, is that the covariance, so if x and y are independent, the covariance of x comma y is equal to the, as the formula indicated, is equal to this, but due to independence, the expected value of the product of the two random variables is equal to the product of the expected values. Now, what is this equal to? Expected value of x is nothing else but the mean of x. Expected value of y is the mean of y. So this difference here is nothing else but 0. So we know that if we have the expected value of, if we have the covariance of two random variables which are independent, then this covariance is going to be 0, and of course that implies that the correlation coefficient is 0. But the converse is not true unless x and y are normally distributed. So here we have the following very important theorem. X and y independent, that implies the correlation coefficient is equal to 0. The correlation coefficient equal to 0 does not necessarily imply independence of x and y. It does imply independence only when x and y are normally distributed. And this is one of the most beautiful properties, and I would say are both normally distributed. This is the beauty of normal distribution. If you know that x and y are normally distributed, then their joint density is also going to be one of the joint normal density. I have this in a video that I have already posted online. Well, theoretically I posted online, I posted the wrong file. So you cannot open the file I posted, but I will correct that mistake. And it talks about the bivariate normal distribution. What is the bivariate normal distribution? In simple terms, two random variables x and y, which both have normal distribution. The bivariate normal distribution tells how they interact. And over there you see exactly what is the role that the correlation coefficient is playing. And from that role, we infer that if rho is equal to 0, then x and y are independent. But that requires that x and y are both normally distributed. Okay, now let's do an example where we calculate with a discrete random variable the correlation coefficient. Okay, so do you remember the problem with the two urns, which was on the homework? Have you returned that homework? You did, okay? Oh. So I'm not going to solve a problem for an outstanding homework and solve it on a video too. That would be too bad. So we have two urns, urn 1, that contains 3 black and 3 white balls, and we have another one, urn 2, that contains 4 black and 2 white balls. Now we cast a 6-side die, and the rule is choose a ball at random from urn 1 if die shows 5 or 6. Otherwise, choose a ball, again, of course, at random from urn 2. And now we have x taking the following values. 1, if you choose a white ball from urn 1, 0 otherwise, and y if you choose, takes the value 1 if you choose a black ball from earn 2. I may be doing a small variation of the problem and 0 otherwise. And the first question, okay, the question that I want to address now is to find the joint density first, and then find the covariance and, of course, the correlation coefficient of these two random variables, x and y. They're simple random variables, so the calculations are not going to be tough. Now, let me just scroll back a little bit and stress something. When we do this calculation in this formula here, in this particular formula, what I have, mean of x and mean of y, those will have to be calculated from the marginal densities of x and y. I may use the word density both for discrete and continuous random variables, but don't worry about that. That's a common expression. If you know that I'm talking about a discrete random variable, automatically you should not be confused by me using the word density. You should automatically understand that I'm talking about the probability mass function. But in all practical aspects of your life, of your scientific life, you will never hear people talking about mass functions. They will be talking about densities. And you have to figure out whether you will use an integral or a sum. That comes from the content we're talking about, from the type of values the random variable takes. The same here. To calculate those standard deviations, you again use the marginal. So let's go down here with these things in mind. Let's go to our example and try to do the calculation. So first step, calculate the joint density. F is the joint density of x and y. So to calculate the joint density, we do what? We do this table here, values of x. Let's leave some space for the marginals here. Values of y, 0, 1. So here are the values of y. These are the values of x. And now, what is the probability that both random variables take the value 1? You remember that? Okay, let's see what is x takes the value 1 and y takes the value 1. If you choose that means that you choose a ball from earn 1 and the ball is also chosen from earn 2. That cannot happen because you cannot at the same time pick the ball from earn 1 or from earn 2, okay? So that's mechanically impossible. So therefore, here you put the value 0. Let's look for that. X takes the value 1 and y takes the value 0, which means this is the probability of choosing a ball. Choosing what ball? Choosing a white ball from earn 1. White from earn 1. And what does y mean to be equal to 0? Y is the otherwise, so you essentially, you see the phrase here, otherwise does not rule out that x takes the value 1. Okay? So it's a more general event, which means that the only thing that is not happening is that you choose a black ball from earn 2. That's what it means here, that y takes the value 0. So essentially this means find the probability that you choose a white ball from earn 1, which is the probability of drawing a white ball from earn 1, draw white ball, given that you choose from earn 1, times the probability of selecting earn 1. Because this event should be interpreted in the following way. Draw a white ball and draw it from earn 1. That's why I use this law here, which doesn't put me in the burden to see whether I have dependence or independence of these events. So what is the probability that you choose N1? 2 over 6, that's 1/3. And the probability of choosing a white ball, look how many white balls you have, 3 out of 6 balls. So you have 1/2 times 1/3, so that's 1/6. So here you will put 1/6. So likewise, let's calculate this value here, the joint density that x takes the value 0 and y takes the value 1, which means that you exactly choose a black ball from urn2. You choose urn2 and you draw from it and you draw a black ball. So again, that would be what? How many black balls do we have in urn2? We have 4 out of 6. So that would be exactly 2/3, 4 out of 6, times the probability of choosing this black ball, choosing this urn2, which is 2/3. So that would be 4 nines. So here you would put 4 nines. Now, you remember that it's more tricky to find this position here, but you have 2 random variables. So what do you know? You know that all of the values of the joint PDF should add up to 1, correct? So what is, you only don't know one value. You know all the remaining values. So what that value would be here? It would be 1 minus 1/6 minus 4 nines. Okay? So that's an easy calculation, yes. From urn1, you draw from urn1 only if you cast a die and you score 5 or 6. So for any other case, you draw from urn2. Any other result, actually. Is it clear? What is 1 minus 1/6 minus 4 nines? What? 7/18. Okay. Do you all agree? Because I haven't made the calculation. So let's put it here, 7/18. So what is the marginal now? Let's calculate the marginal of y. So here I'm calculating the marginal of y. Here I'm calculating the marginal of x. What's the marginal of y? We have 7/18 plus 1/6. So that will give us 10/18. Am I correct? Am I right? And of course here you have 8/18. And over here you will have 15/18. And of course here you have 3/18. And everything adds up to 1. So I have the marginals of x and y. Now let's find, since we have the marginals of x and y, and you don't have anything else to do, let's calculate the mean of x. I'm trying to keep everything in one table. The mean of x, that will be equal to what? We take the marginal of x. So here are the values of the marginal of x. These are the values we will take. So you have, this will be 0 times 15/18. Okay? Is it clear why I'm taking 15/18? Because 15/18 is the value of the marginal of x when x takes the value 0. Plus 1 times 3/18, so it will be 3/18. And the mean of y is going to be likewise given equal to 8/18. Well, let's simplify this fraction here. This is, well, just keep them like that, but we'll need now a calculator. How do we find now sigma of x? Or let's find the variance of x. How do we calculate the variance of x? What is this equal to? E of x squared minus the mean of x squared, okay? What do I need to calculate this, E of x squared? How do I calculate it, in other words? Sigma x squared, which are the values of x, 0 or 1, so you have only two values, times the marginal of x, minus the 3/18 that you have here. So this is going to be the variance. So now you have two values here. 0 square times the probability that you have 0, which is 15/18, plus 1 square times 3/18. I still have the table here on the top so you can see it. It barely fits now on the screen. So that minus 3/18 square. So this is going to be equal to 3/18 minus 3/18 square, which is 3/18 times 1 minus 3/18. You see I still do calculations the old nice way. That will be times 15, so that would be 45 times 18 square. I just keep it like that because I have the variance. Now, what is the standard deviation of x? That's the square root of the variance. Okay, so I'm taking the square root of the variance, so the square root of 45. The square root of 18 square is 18, so that's why I kept it without calculating it. I knew it would come out easy. And what is factorize 5? It's 45, it's 9 times 5, so that will be 3. The square root will be 3 times the square root of 5 divided by 18. Let's simplify a little bit. Square root of 5 divided by 6. Any questions so far? Because the next thing to do would be to find the mean, the standard deviation of y. Standard deviation of y will be the variance of y. Square root, well, let's find the variance of y. The variance of y will be e of y squared minus the mean of y squared. So that, let's look at the values of y. The values of y are 2, 0, and 1. So we only need to take 1 squared times 8 times 8, 8 over 18, because the other value, 0 squared, will give us 0. So whenever you multiply with its probability, it's going to give you 0. Is it clear? It's the same. It's one of the same here with just of here with just different values. Is it clear? So that will be 8 times 18 minus the mean of y, which is 8 times 18 squared. So again, we have the same type of calculation, 1 minus 8 times 18. So that will give us 18 squared, 8 times 10, which is 80. We barely have 81 here. So the standard deviation of y then will be the square root of 80 times divided by 18. Any questions? Okay, so let's leave it like that. So what is the covariance now? To find the covariance of x and y, what do I need to find? I need to find e of x times y minus the mean of x times the mean of y. What is e of x times y? Multiply all the values of x and y, okay? X times y. So that would be here the sum of x times y. It's a double sum. X goes from 0 to 1, y goes from 0 to 1, times the mass function, the joint mass function. So let's see the values of 0 and 1. They are up here. Two of the values are equal to 0. So whenever one of the two takes the value 0, no matter what the value the other one takes, the other random variable takes, the product is going to be 0, correct? So when do you have a non-zero value when you multiply the products, the values of x and y. When both take the value 1, when both take the value 1, and when both take the value 1, the probability, that probability is equal to 0, okay? So here you have a much easier computation, and let me correct my mistake here, minus the mean of x times the mean of y. So here everything is 0. So you have 1 times 1 times the probability that you get 1 times 1. Let me write it so that you won't get confused at the end of the day. So this is, let's put the mean values. I forgot them. 318 times 818. 318 times 8 over 18. So this is also equal to 0. So at that product, the covariance of the two is going to be just negative. You see, it's a negative value. 3 times 8, 24, negative 24 over 18 squared. That's the covariance of the two random variables. So, are the two random variables independent or not? And why? Why? Huh? No, we didn't calculate that, so how do you know that? Quick answer, why are they not? What did I say before? Look, let's scroll up. If they're independent, what should be the correlation coefficient equal to 0? Which means also the covariance is going to be 0. Why? Because the covariance is defined as from this equation here. All right? Therefore, for rho to be 0, the covariance has to be 0. Now we found that the covariance is not equal to 0. Therefore, x and y are not independent. Short answer. What is the correlation coefficient between the two? Well, just take the covariance and multiply, divide it by the product of the correlation of the variances. So let's use what we have here, this one and this one. So we have 3 times the square root of 5 times square root of 80 divided by 18 squared. Let's simplify the 18 squared. You have negative 24. 3 times the square root of 400. What is the square root of 400? 20, correct. So you have 24, negative 24 times divided by 3 times 20. Well, simplify and you got a cleaner number here. Negative 8 over 20, you can simplify it by 4 again, and that's the answer to the problem. Was that problem difficult? Or are there any questions so far? Some people look at me very, very skeptically. So properties of mathematical expectation for two random variables, we show that the covariance x times y then will be the covariance of x comma y plus the product of the means. Okay, and now there is a very interesting property that I want to talk about. If x and y, let me write it with, if x and y are independent, then the standard deviation of the sum squared, or let's say, let me write it the variance, then the variance of x plus y is equal to the variance of x plus the variance of y. This is called Pythagorean theorem, because that's what it is. So that's the Pythagorean theorem. In other words, I can write it that the square of this is equal to the sum of the squares of the standard deviations. But it requires independence for that to be true. Okay?
Is that the same theorem as A squared?
It's pretty much the same, yes. It's pretty much the same. Okay? And if we have the expected value of A times X is equal, when A is a constant, is A times the expected value of X. So that's a constant. Recall also that the expected value of the sum of two random variables is always the sum of the expected values. That works for all cases. So this is also universally true. And if we do the variance, that I can actually show that. If we take the variance of A times X, that's the expected value of A times X squared, all of it squared, minus the mean of which random variable? A times X squared. So what is A times X squared? What is this thing equal to? This is the expected value of A squared times X squared, algebra. What is the mean of A times X? This is A times the mean of X. Now, this is a constant, and according to what I have said, can go out of the absolute of the expected value. So you have A squared. Now factor out A squared, and you have the variance of X. So the standard deviation of A times X squared is equal to A squared times the standard deviation of X squared. And if I want to translate this to standard deviations, then that would mean A times standard deviation of X. Okay? So here is my first new definition. Let's take 10 random variables that are independent and identically distributed. What does identically distributed mean? That means ID. There's an abbreviation here, ID. Identically distributed. It means that all have the same distribution function, or equivalently, all have the same density. So if all have the same density, what do all have? The same mean and the same standard deviation. And let's call the mean me and the standard deviation sigma, which are common. What is the mean of all of them? The mean of the sums. What should I do? What's the property that I do? When I sum two random variables, the expected value of the sum is the sum of the expected values, okay? Let's write it again here. So let's transfer that. Let's translate that to this particular example. So this will be the sum of the expected value of the first random variable plus the sum plus the expected value of the second plus the expected value of the 10th. But all of them have the same, equal to me. So it will be summing me 10 times. So that will be 10 times me. Okay? Nothing difficult so far. Now let's go to the variance of all of them. The variance of the sum. What do I know about the variance of the sum? The Pythagorean theorem. But what do I need? I need independence between the random variables. Correct? But here I gave you the independence. They are independent from one another. So therefore the sum, the variance of the sum is the sum of the variances. Likewise. And all of them have variance equal to what? All have standard deviation sigma. So what is their variance? Sigma square. So all of them have variance 10 times sigma square. Okay? Now let's take a new random variable, which I call x bar, and this is the sample, this is the average of them. I take the sum and I divide it by 10. What is the mean of x bar? Mu. 10 times me is the sum, the expected value of the sum of all of them, divided by 10, okay? So that would be equal to me. Let me write it explicitly. This will be 1/10 times the expected value of the sum of these 10 random variables, and of course that will give you 10 times me. We just calculated here, divided by 10, so that gives you me. What is the standard deviation of x bar? Let's do the variance of x bar. Okay, it's the variance of x bar. So this is the variance of 1/10 times the sum. So what do we know about the variance here? You see this property? We take A, which is here, that's the 1/10 times the sum. So that 1/10 will become 1/10 squared. So this is equal to 1/10 squared times the variance of the sum. We calculated the variance of the sum. So what is this equal to now? It was times 10. It was 10 times the sigma square, okay? And you see that 10 with 10 square will cancel, so it will be sigma square divided by 10. So what's the standard deviation of x bar? The standard deviation of x bar will be now sigma divided by the square root of 10. And here is an important property of what we call the arithmetic mean of a number of random variables which all have the same distribution. This is also called sample average. So x is called sample average. And what is a random sample? A set of independent, identically distributed random variables is called a random sample. So here I had a random sample of 10, of size 10, as we call it, because I had 10 random variables, all independent. from one another. That means random sample independence, and all identically distributed. So all properties, including densities, are all the same for all of these random variables. Why? Because it's a sample from the same population. And this is something I will be discussing more in the lectures next week. So the sample average has standard deviation, which is smaller, much smaller than the original standard deviation. And that's the property. The arithmetic mean, as we call it, the sample average, behaves better than the actual observation. That's why we sometimes use the sample average. It's not very difficult to understand. If you put individual people to sing, they will not probably sing as well. But if you put them in a choir where all the voices are added up, so you get an average of all the voices, then the choir sounds much better than the individuals who are in the choir. That's a very, very important property which arises in many aspects of science. Okay, now I'm going to do a few more problems in this video, but I'm not going to do them now, so I'm going to pause the video. So problem one, I'm also going to do an application of problem one. Suppose that x and y are two random variables. I don't need to specify whether they are continuous or discrete. And we know somebody gave us, let's say, exactly this information. The mean value of x, the mean value of y, the variance of x and y, and the covariance of these two. Find the variance of x plus y and the standard deviation of x plus y. Well, of course, if we find the variance of x plus y, then the standard deviation is going to be only the square root of the variance of x plus y. So let's see how we'll find the variance of x plus y. First of all, we do not know that x and y are independent random variables. Therefore, we cannot use the Pythagorean theorem. So we cannot use this. That would be a terrible mistake because it requires that both random variables are independent. Since we're not given this information, we'll have to use the definition. So this is going to be the expected value of x plus y squared minus the mean value of x plus y again squared. Well, let's work a little bit on the expected value of x plus y. This is e of x squared. Now, I have to expand this, and simply what I'm doing is that I'm using the algebra because x and y are random variables. Therefore, when I write x plus y here, what I mean is I create a new random variable which takes as values sums of values of x and y. So these values, when you will expand them. When you will expand your sum to the square, you do the algebra. That will give you three random variables, actually these random variables, x squared 2 times x y times 2 times x times y and y squared. So this is going to be value of x squared, value of x times y, value of y squared. And the random variable of these, the expected value of these three random variables, I'm now called to find. And of course, to do that, I will apply the rules for the expected, with the algebraic rules of that govern expected value of the sum. Now, this is also here expected value of x plus y, and we know that expected value of x plus y is expected value of s plus expected value of y. Therefore, inside the square, I will have mean of x plus mean of y squared. Now let's continue. The expected value of a sum of three random variables is going to be the sum of their expected values. Here I have numbers, the mean value, the expected value of x and the expected value of y squared. So this will give me this is nothing else but a plus b squared. And now this 2, which is a constant, can be pulled in front of this. But at the same time, I can begin grouping things here. So I will group this with this. And I will do the same with the expected value of y squared. After pulling 2 in front of the expected value, here I have 2 times the expected value of x times y minus 2 times the product of the mean values of x and y. And of course, I can factor out 2 here. Let me do it directly, so I can have this. And if you see, the first parenthesis here is the variance of x. The second parenthesis is the variance of y. And the third parenthesis is the 2 times the covariance of x comma y. So if I have all of these values, if all of these values are given to me, then I'm fine. I can calculate that. So, for example, for these particular values, the variance of x. So in problem 50, this was problem 50, but I paraphrased it. From the pre-actuarial exam. Using the data from this problem, I'm not fully solving this problem. This problem actually requires the use of the central limit theorem, and we haven't done this theorem yet. We'll do it after. Actually, we will do it on November 1st, the day you will have your quiz, your long quiz. Sorry, this is the variance. I want it here. So if I use the data from this problem, I have that the variance of x is equal to 50, the variance of y is equal to 30, and the covariance is 10. So what I will do here is to use these values. 50 plus 30 plus 2 times 10, so that gives us 100. And so the standard deviation of x plus y is equal to 10. So here you show an example where I calculate the variance of the sum of two random variables which are not independent. If they're independent, of course, the covariance is zero, and what remains here is the Pythagorean theorem rule. So I generalize the Pythagorean theorem here without being in the need to assume any independence. Now let's go to another problem. I will do one of the problems in the book, so I'm moving now to page 179, doing problem number 2. And again, this is from the book. We have x that has exponential distribution with mean equal to 500. So we have x exponential with mean. Mean is what the book calls b equal 500. Now recall when I did the calculation in the class, if I use f sub x to be the PDF of the exponential, and I use this notation for the exponential with x positive, then the expected value of x as we calculated is 1 over a, and this is the mean value. So this 500 that you have is equal to 1 over a, and therefore this a is equal to 1 over 500. So now having the parameter that I need for this random variable, the exponential random variable with mean, I can write down the formula for this random variable. It's exactly this. And of course the PDF of x is equal to 0 if x is less than or equal than 0. Oh, that's the correct notation. Now the problem is asking me to find the probability, the conditional probability that P will be greater, that X will be greater than 1,000, given that already X is greater than 500. So what I do here is essentially I use the rules of the definition of conditional probability. So I have two events, event A and event B here. So that will be the probability of A intersection B divided by the probability of B. And of course, if you see the probability of X being greater than 1,000 and X being greater than 500, of course boils down to X being greater than 1,000, because X being than 1,000 supersedes this inequality. This will be divided by the probability of the condition, which is X being greater than 500. And therefore I have that this is the probability that X is greater than 1,000 divided by the probability that X is greater than 500. And let's compute these probabilities. This is 1 minus the probability that X is less than or equal than 1,000. And this is 1 minus the probability that X is less than or equal than 500. And since X takes values, since the PDF is 0 when X is negative, I integrate here from 0 to 1000 the PDF, and here I integrate from 0 to that should be 1000 to 500, again the PDF of X. So let's do this computation. This is 1 minus from 0 to 1000. I can also do, I will not give me too much, over 500 e to the negative x over 500 dx. So the antiderivative of this integrand is e to the negative x over 500, and I'm taking this from 0 to 1000, and again from 0 to 500. And of course, if we complete this calculation, we'll finally have 1 minus. I'm sorry, I forgot the negative sign here. Thank you. Which I actually need to make this work. Editing is not that easy sometimes. So this is 1 minus e to the 1000, negative 1000 over 500. 1 minus e to the negative 500 over 500. So this is e to the negative 2 divided by e to the negative 1. And if we reverse things, this is e divided by e squared, so it's 1 over e, this probability. So we calculated this probability. Now, actually, in the process of doing this, I have already answered this question 1, question B, because question B was exactly to show that this conditional probability is equal to this probability. I went further on and solved the whole, calculated this ratio, because I wanted to work here with probability so that you know what I would be doing. Now let's next I work a little bit on problem number 4. Or let me do actually problem number 5. Number 5, 3, 3, 3. It's problem 5 in the same section. That's on page 179. In this problem, we have some alpha particles. X is the number of alpha particles of carbon 14 per second that are being emitted, that are being counted by a counter, by a Geiger counter. Now, typical when we have particle counts, we use the Poisson distribution. So X has a Poisson distribution. Actually, the problem is giving you that it has the Poisson distribution. and it has a Poisson distribution with mean 8. What is the mean of the Poisson distribution? This is exactly the lambda of the Poisson distribution, which is the rate here of the Poisson. So with this rate, now I want W to be the time, the waiting time until the first, I'm doing a variation of the problem, until the first arrival of a particle at the counter, at the Geiger counter. So if the particle arrives at the Geiger counter, it will be counted. What is the distribution of X? I want to find the distribution of X. Essentially what I'm asking you is to find the PDF of W. Find the density of W. So since X has a Poisson distribution and W is the waiting time until the first arrival, we know that W has an exponential distribution. Now we made we made an assumption in actually we made a derivation, and when we made the derivation I told you the following. The rate of the Poisson is actually 1 over the rate of the Poisson is equal, when we had the Poisson process, is equal to the mean of the exponential. So if the rate of the Poisson, here you have a Poisson distribution, and that Poisson distribution says that says the following: we have a mean of 8. So that means a mean of 8 particles per second. So this can also be considered as rate. So this lambda equal 8 is 8 particles per second, because it says let x be the number of, the problem says precisely, let x equal the number of alpha particle emissions of carbon-14 per second. Therefore, we know that this lambda is exactly 8 particles per second. So lambda is 8 particles per second. So the rate of this emission is 8 particles per second. Therefore, the mean arrival time, which is the mean of the exponential, is going to be 1/8 of a second, is the mean of the exponential. So we have an exponential with mean equal 1/8 of a second. So what shall we put here? F of W. So the mean, which should be, look how the exponential is going to be. Let's look at it again. It's this one here, and the mean is 1 over A. So this 1 over A is 1/8 of a second. So what does give you? What A has to be? A has to be equal to 8. So here you have that f of x is equal to 8 e to the negative x over 8 when x is non-negative, and 0 if x is negative. That's the correct way to say the PDF. Of course, this second branch can also be omitted because waiting time always is counted with positive time. So you can leave that here. So if I want to find the probability that W is greater than the W, the exponential distributed, is greater than 0.75 seconds, and then I will take the integral, since I have the exponential 0.75 here, and that will be 8 e to the negative x over 8 dx. And you do this integration and you solve the problem. Now, in the book, the problem is being solved is being asked in a different way. Assume that W be the waiting time in seconds before the second count is made. Now, arrival time, or excuse me, waiting time until the nth success, whatever is success, in a Poisson process is modeled by the gamma distribution. So to find this probability, to find the probability model for this now W, this version of W, so W here is waiting time until the second contact, second particle arrives. At the counter has gamma distribution. Because the emission of particles has Poisson distribution. Actually, the arrival, the number of particles that arrive at the counter has Poisson distribution or Poisson process. Here it was the Poisson, directly we had the Poisson distribution because this X was X of window of observation of 1 second. That's why we directly went to the Poisson distribution. So waiting time until the second particle arrives has gamma distribution because X has Poisson distribution. And now I have to show you how to use the gamma distribution, the formulas for the gamma distribution. The formula for the gamma distribution is given in table 331. So look at table 331 on page 178. And now let's see how we use this table, which says that f of W is going to be equal to 1 over gamma of A times beta of A. I will explain now how to find those parameters. X to the alpha minus 1 e to the x over beta. So now let's see how we find the values for alpha and for beta for this particular problem. So here, when we use the gamma distribution to model waiting time until the nth success, the gamma distribution that we have to use has alpha equal to n, and beta, the beta parameter, the beta parameter, this is not beta, it's actually beta, like your CV, beta. In Greek, this is going to be 1 over the rate of the Poisson. Let me write it here properly, 1 over the rate of the Poisson. So this should be 1 over, the beta should be 1 over the rate of the Poisson. So here my rate of the Poisson is exactly equal to 1/8 of the particle. This is something we calculated before. So in my example, alpha then, since I'm waiting until the second arrival, alpha should be equal to 2, and beta will be 1 over 8 of a second. So I would have had the f of w of x would be equal to 1 over gamma of 2. I will tell you exactly what gamma of 2 is going to be. 1/8 square x to the 2 minus 1 e to the negative x over 1 over 1/8, which would give me the and I think I made a mistake here in the previous problem when I put the, let me correct my mistake. The rate was 1/8, therefore I should have had alpha times x, it's 8x, not 1/8. And here I also have the same, I just found this 8x. In the exponential and the gamma, these should be the same here. So this should be 8 times, yeah, that here I wrote it nicely. So this is going to be the following. Now, gamma of n is equal to n minus 1 factorial if n is a positive integer. In general, the gamma function generalizes the concept of the exponential, the concept of factorial. That's why it ends to be the factorial for integer numbers. Now 1 over 8 squared, that's not difficult to calculate, so therefore this one would be 1 factorial. So this will give you 8 squared times x times e to the negative 8x. So this is exactly the Poisson, this is exactly the gamma distribution that we have. And in this case, when you have this type of gamma, is not very difficult to calculate, to make all of the calculations. You need, if you want to calculate probabilities, then you would need to do exponent. You would need to do essentially integration by parts. So if I have to calculate what is the probability that W is going to be less than or equal than 0.75, then what I need to do is to integrate. Of course, again, x is non-negative. I integrate from 0 to 0.75 the PDF. Well, we did this kind of integration before, so I'm going to use here everything that I'm given. So I have 8x, let's put it in a parenthesis, I have already hijacked 1/8 from 8 squared, e to the negative 8x, my dogs are barking, and now I'm making the substitution that 8 times x is going to be y. So this integral is going to be from 0, 8 times 0, 8 times 0.75, y e to the negative y dy. And so this is from 0 to 6, y e to the negative y dy. And now I'm doing the, let me stop here to do the integration by parts. So I'm taking y e to the negative y dy. Integration by parts will give again y e to the negative y derivative dy. So that gives this y plus negative e to the negative y prime dy, and all this gives negative y negative y plus 1 e to the negative y. So we put this here, from 0 to 6, and of course this will give 1 minus 7 e to the negative 6. And you just leave that probability right there. You don't have to calculate it. And as you see, this is a significant probability. This is going to be a small number. This probability is close to 1. Why is it close to 1? Because the mean value of the gamma, since the mean value is equal to alpha times beta, here you have alpha to be equal to 1/8. So the mean will be 2/8, 1/4, which is 0.25. So if you want waiting time to be until 0.75, you wait quite longer than the mean, and therefore this tells you that the probability that you will have two particles arriving in waiting time which will not exceed 0.75 is quite significant. Well, with this, I'm just stopping here with this example. I don't encourage you to do problem number 3. Just try to avoid it. Work on problem number 4. On problem number 4, again, you have the rate of a Poisson process. So you have a rate of a Poisson process which says 0.75 calls per minute. 3 calls per 4 minutes, which means 0.75 calls per minute. So if you want to wait to see the W, to denote the waiting time in minutes until the second call arrives, then again you have a gamma distribution. If I say what is the waiting time until the first call arrives, then you have an exponential distribution, because if I say until waiting time until the first call arrives, this is waiting time until the first success in a Poisson process. And what would be the mean in that case, the mean of the exponential? It would be 1 over the rate of the Poisson. So it will be 4 over 3 minutes. So your 1 over alpha is going to be 1 over your 1 over alpha will be 4/3. So in problem 3, in problem 4, if W, I'm using a variation, W waiting time until first call enters the switchboard. So W has exponential with mean 4/3 of a second, 4/3 of a minute. So in this case, 1 over alpha is 4/3, and therefore alpha is 3/4. Alpha is the rate of the Poisson. That's why you see this coincidence with the rate of the Poisson. So in this case, the f of w of x would be alpha, the 3/4, times e to the negative a times alpha times x. So that alpha here would be 3/4. And always the sanity check says that this has to be equal to this in the exponential. If you're not given that your problem has a Poisson process and you're asked about waiting time, then you should be able to see whether you should be able to argue whether it is reasonable to assume that you have a Poisson process in what is being described, and then model the waiting time after gamma or after the exponential, which is a special case of the gamma distribution. Actually, the exponential is the case of the gamma distribution with alpha equals 1. Now I'm moving to the last problem I would like to solve in this extra class that we have in extra class time here. And I'm going to solve a problem I'm going to solve a couple of problems with a normal distribution. First, I would like to solve a problem. So let's go now to section, go to problems 3.2. And let's solve a problem which is similar to 2D. So suppose that I have X, which has a normal distribution with mean 25 and sigma equal to 4. And suppose that I want to find the probability that X minus 3 is less than 2.1. Of course, if we do the algebra here, because that's the first thing we have to do, get rid of the absolute value, then you would have that negative 2.1 is less than X minus 3 less than 2.1. You know that from college algebra. And now I have to see what is the lower value, the lower range for the X that is prescribed by this inequality, and the upper range for X. So I move 3 to all of the three sides, to the left and to the right. So this tells me that if X minus 3 satisfies this inequality, then 3 minus 2.1 will be less than X than 3 plus 2.1. So this is X being less than 0.9, being less than 5.1. So now I'm going to the standardization. So standardize now. Subtract from all three sides the mean and divide by the standard deviation. So you have, this is the probability of 0.9 minus 25 divided by 4 less than X minus 25 divided by 4 less than 5.1. So this is going to be negative 24.1 divided by 4. Now, when you subtract from the normally distributed random variable the mean and you divide by the standard deviation, this becomes a new random variable which has standard normal distribution. That's why I denote it by Z. So I put Z here. And I know that Z has standard normal distribution. And now you can proceed accordingly. We have shown how to do that in class. This is exactly going to be phi of minus 19.9 divided by 4. This may be a very small number according to the tables. And what is phi? This is the CDF of the standard normal distribution. And you find it in the tables in the book. I will conclude with one problem here, with another problem. I will do problem 8. The average weight of a certain brand of a refrigerator is 31 pounds. Due to variability in raw materials and production conditions, weight is a random variable, and we assume that this random variable has normal is normal with standard deviation equal to 0.5 pounds. So X is the weight of the refrigerator, and we assume that the problem is telling us to do so, that it has a normal distribution, but we're only given here the standard deviation, or are we given also the mean? We need the mean now for X. Let's look at the problem again. The average weight of a certain brand of a refrigerator is 31 pounds. So the problem, by telling us the average weight of a certain brand of refrigerator is 31 pounds, the word average means mean. So we know that this is that X has a mean of 31 pounds. The standard deviation is 0.5 pounds. So now we want to find the probability that a refrigerator is heavier than 32 pounds. So once again, we subtract the mean from X, we divide by the standard deviation. So we do that also on the right hand side of this inequality. So since X has normal distribution and we subtract the mean and we divide by the standard deviation, this fraction is equal to Z. So this is equal to 1 divided by 0.5. So we're looking at Z being greater than 2. And of course, we know the values. This would be 1 minus P of the probability that Z is less than or equal than 2. So this is 1 minus the value of the CDF of the standard normal at 2. So let's look what this value is. In order to solve the problem, now we go to pages to the tables here. Go to page 569 where you have the positive values of Z, and you see Z equal to 2.0. This probability is equal to 0.9772. And you do the math and you find the probability. So let's say now, let me make a small variation of the problem. Suppose that Y is the weight. We don't buy one refrigerator, but we buy two refrigerators of the cumulative weight of two refrigerators. What is the mean weight of these two refrigerators? What is the average weight of these two refrigerators? If I want to do this, then it would be this 2 times X, because I have two refrigerators. Their weight is twice the weight of one refrigerator, and since the mean X is normally distributed with mean equal to 31, this is 2 times E of X, so this is 2 times 31, so it would be 62 pounds. That was a small variation of the problem, a small tweak that I just put as a mind teaser there. And with this, I'm concluding this session. Please also go and look at problems in this section. 3.2, those are not difficult problems, but I expect you to be able to solve these problems. And please be prepared for next week. Thanks a lot and have a nice week.